calculating the composition of a buffer of a given pH. So essentially what this type of question is asking us to do is to use our friend, the Henderson-Hasselbalch equation, which allows us to calculate the pH of a buffer. And this time we are aiming for a specific pH, and in this case our buffer is a weak acid with its conjugate base dissolved in it. And we have the concentration of that weak acid. So essentially what we're going to have to do is rearrange and solve the Henderson-Hasselbalch equation to find an unknown concentration of base. So we can rearrange that. So let's have log of the concentration of our base over the concentration of our acid on one side. And then that is going to be equal to pH minus pKa. We don't have pKa, but we have Ka. So we're going to be able to calculate that pretty straightforward. And then if we do 10 to the power of each side to get rid of the log, we're going to end up with concentration of base, whoops, over concentration of acid is equal to 10 to the power of pH minus pKa. In fact, we can even rearrange that further so that the concentration of base is our subject, because that's what we are going to be solving for. And of course, that will be the conjugate base of our weak acid in our buffer solution. So that is going to be equal to 10 to the power of pH minus pKa. I suppose we should probably have brackets in here just to be sure what we're doing, and then multiply that whole thing by the concentration of our weak acid in our buffer. Okay, so what do we know? What do we need to find out? We've got to find out pKa. We've got our concentration of our acid, so then we should be able to work out what concentration of our base we should have. So pKa is minus log of Ka. So you can either just stuff that straight in your equation or calculate it separately. So Ka for my nitrous acid was 4.5 times 10 to the power of minus 4. And that shakes out to be about 3.3, and friends, 3.3467, and that supports what we know about buffer solutions and selecting the correct buffer, because you should pick a buffer where the pKa of your weak acid or your weak base, depending on what kind of buffer you're making, is within 1 pH unit of the pH you're trying to maintain. So we are fitting that beautifully. All right, so let's calculate the concentration of the base that we should have. And just to remind you, we have a weak acid, nitrous acid. So its ionization reaction with water is going to produce the conjugate base, the nitrite anion. So when I'm talking about conjugate base, in this case, that is what I'm talking about. And then the water will accept that proton to form hydronium. So this is our equilibrium that we're describing for our weak acid component of our buffer. And the salt in our buffer is potassium nitrate, which is a soluble salt, so that is going to break apart completely into the potassium cation, which is a neutral cation because it's the counter cation of a strong base, and the nitrite anion, which, bingo, that is our conjugate base of our nitrous acid. So the conjugate base of a weak acid is of itself going to be a weak base. So there is our basic salt, potassium nitrite. So this is the common ion in between our dissociation of our weak acid and the dissolution of the salt. Okay, so this is the concentration of base that we're solving for in the Henderson-Hasselbalch equation. So I'm going to go right ahead and write concentration of, in this case, the nitrite ion. So that is going to be 10 to the power of pH minus pK. So the pH of the question is 3.06. pKa that we just calculated was 3.3467. And then all y'all will be multiplied. I guess I can do those kind of brackets. Those ones are fancy. All y'all is going to be multiplied by the concentration of my weak acid, which is our 1.70 molar of our nitrous acid. So that is going to give me my concentration of the nitrite anion, and that comes out to be 0.8786 molarity, but we haven't quite answered the question fully. So that is my concentration of nitrite that is required. But this is the only like new stuff as far as Gen Chem 2 goes, because now we're just talking about converting concentration of a solution and we have a known volume. We have 250 milliliter volume to a number of moles. So our plan is going to be that we're going to go from the concentration of my NO2 minus and use the volume of that to get to my number of moles of my nitrite ion, which is then going to tell me my number of moles of potassium nitrite that I need to weigh out, and then I'm going to want to get to my mass of potassium nitrite. So what things do I need to gather together? I need to gather together my volume of solution, which is going to be the 250 mils. So each of these conversions is going to need some kind of factor. So concentration to moles is going to use volume. And of course, I've got to be careful. I've got to get that from milliliters to liters as well. So make sure you've got the right units there. And then moles of nitrite to moles of potassium nitrate. Well, we can get that mole ratio from having written out the dissolution. In this case, it's a 1-to-1 ratio. For every 1 mole of potassium nitrite that dissolves, that will yield 1 mole of nitrite anion. So you do have to always watch for the stoichiometry of that. And then finally, we're going to need our molar mass of potassium nitrite to convert between mass and moles. Okay, so to get from moles to mass, so 1 mole of KNO2 weighs exactly 80 something, 85.1035 grams, so the molar mass in grams per mole. So now we've got all those together, we can just do a moles calculation just like we did in Gen Chem. So I'm going to rewrite 0.8786 in terms of moles per liter because that makes it easier to see with the units. So concentration times the volume, which is 250 from the question. Of course, we got a little bit of a problem there because milliliters and liters are not compatible. So I'm going to have to convert milliliters into liters. 1 milliliter is 10 to the minus 3 liters. Okay, so what have we got? Liters cancel, milliliters cancels. I've got my moles of nitrite, and you know what? I'm going to be very pedantic here and put moles of the nitrite anion. So now I need to convert moles of nitrite to moles of potassium nitrate. So use that mole ratio for, and of course it's 1-to-1, but please don't be lazy and leave it out because mole ratios are not always 1-to-1. So for every 1 mole of nitrite anions, that's coming from the dissolution of 1 mole of potassium nitrate. So now we've got our number of moles of potassium nitrite. And then lastly, we're going to use the mass, the molar mass to convert to mass in grams. So 85.1035 grams for every 1 mole of potassium nitrite is the molar mass. So let's just check that we've performed all those conversions correctly and that everything is cancelling out as it should be. So liters cancels out. That should be 10 to the minus 3 liters. I must have missed it when I was typing. This is why it's good to check, right? Milliliters cancels, moles of nitrite cancel, moles of potassium nitrite cancel, giving us a mass in grams. And if I put this in my calculator correctly, that is 18.70 and change grams. We were asked to 2 significant digits. So that would just be 19 grams to 2 significant digits. So there we are.